Have you ever really stopped to think about what's happening inside the computer that you're using right this second? Well, today we're going to digitally unbox it. We're going to peel back all the layers to see how your simple clicks turn into the incredibly complex calculations that pretty much power our entire world. You know, if you've ever gone shopping for a computer, you've definitely seen a spec sheet just like this one. It's just a wall of jargon, right? Gigahertz, DDR3 ST-RAM, L2 cache. It's all a bit much. So what does any of that stuff actually mean? Well, by the end of this, you're going to have a much better idea. And that really is the big question, isn't it? How does this box of wires and circuits translate our commands into, well, everything? From emails to epic video games. I promise you, it's not magic, but it is an unbelievably clever system. So let's start by taking a look inside. All right, so what's actually in there? Before we even get to the physical parts, we have to understand two huge ideas that really define what a computer even is. First things first, we need to get a handle on two key concepts. And the best way to think about it, it's like building a house. Computer architecture, that's the architect's blueprint. It lays out what the computer should be able to do. But computer organization, that's the actual construction. It's the physical wiring and the circuits that bring that blueprint to life. One is the plan, the other is the reality. When you boil it all down, every single computer, from a massive supercomputer to the smartphone in your pocket, has just three essential parts. You've got a processor, which is the brain. You have memory to store information. And you have an input/output system. We just call it I/O, which is how it talks to us and other devices. That's it. Processor, memory, and I/O. All those crazy specs from before, they're just describing different versions of these three things. Okay, now here's where it starts to get really cool. See, a computer isn't just one single thing. It's actually a stack of layers, with each one building on the one right below it. And this idea is absolutely crucial. A computer is a hierarchy of levels. At the very top, that's the user level. That's you running your favorite apps. And way down at the very bottom is the digital logic level, the actual physical circuits. For your mouse click to do anything at all, it has to travel all the way down this stack and back up. So let's take a quick elevator ride down this skyscraper. We start at the top, the user level, where you are. A programmer, maybe one level down, writes an app in a language like Java. That code then gets translated down through the layers. It hits the operating system, like Windows or Mac OS, until finally it becomes nothing more than simple on-off electrical signals at the very bottom. This whole concept is called abstraction, and it's the secret sauce that makes all this complexity manageable, because each layer only has to talk to the one right above or below it. So now that we're down at the hardware level, let's look at the master plan that nearly every modern computer is built on. It's called the von Neumann architecture, and it was a total, absolute game changer. You see, before this brilliant blueprint came along, programming a computer was, well, it was a nightmare. To solve a new problem, you had to physically unplug and replug tons of wires and flip a bunch of switches. I mean, can you imagine having to rewire your calculator every single time you wanted to switch from adding to subtracting? It was unbelievably slow and inefficient. The absolute genius of the von Neumann model was to treat the program's instructions just like data, and then store them both in the same memory. This meant you could change the entire program without ever having to touch a single wire. This idea, the stored program computer, is the foundation of pretty much every single device we use today. So how does this machine actually run a program? Well, it uses a simple but relentless loop. It's called the fetch, decode, execute cycle. You can think of it as the computer's heartbeat. First, it fetches an instruction from memory. Then, it decodes what that instruction means. And finally, it executes the command. And it does this billions of times, every single second. We can actually see this cycle in action right here. The CPU's control unit, it acts like a traffic cop, reaching into memory to fetch the next instruction. Once it's decoded, it sends the task over to the arithmetic logic unit, or the ALU. That's the part of the CPU that does all the actual math and logic. And this simple loop is what brings the whole system to life. And hey, when a spec sheet says quad-core, it just means you have 4 of these CPUs all running this cycle at the same time. See? It's starting to make sense. Okay, so we've got a CPU to do the thinking, and we have memory to store the information, but they're totally useless if they can't talk to each other. So how do all these separate parts actually connect and pass data back and forth? Well, the answer is something called the system bus. And honestly, the best way to think about the bus is as a digital highway. It's a shared set of electrical pathways that connects all the major components, letting data travel between the CPU, the memory, and all the I/O devices. And because every major component plugs into this one shared highway, it acts as the central backbone for the entire machine. This shared connection is what lets the CPU grab instructions from memory or send a picture to your screen. Without it, every part would just be an isolated island.
Now, this digital highway has three main lanes. You've got the address lines. They're like the street address on a package. They tell everyone where the data is supposed to go. Then you have the data lines. These are the trucks on the highway carrying the actual bits and bytes. And finally, the control lines. They're the traffic signals, managing the whole flow. And remember that spec, DDR3 SDRAM? That just refers to the type and speed of the memory chips that are feeding data onto this highway. It's all connected.
All right, we've journeyed all the way down to the level of wires and tiny logic gates. Now let's zoom back out and put this whole puzzle together. So here's the bottom line. When you click your mouse, you are kicking off an incredible chain reaction. Your simple command travels down through that skyscraper of layers we talked about, from your application to the operating system, all the way down to the machine code. Then, the CPU uses that bus to fetch and execute instructions, and the result travels all the way back up those layers to appear on your screen, all in a tiny fraction of a second. It's amazing. So we've gone from a simple click all the way down through these layers of abstraction to the hardware itself, hardware that runs on a blueprint designed decades ago. It's an incredibly powerful model, for sure, but it's not the only way to build a computer. So now that you understand the basics, the question is, what do you think comes next? What's going to be the next great leap in computer architecture that changes everything all over again?